Welcome to section 16.1. Okay, gentle people, throughout the Chem 1 series, what we've been talking to you guys about are some things called intramolecular forces. Now, intramolecular forces gives us an idea how molecules are put together, i.e., they are talking about chemical bonds. So if I were to look at the molecule H2, what you guys would say is that there's a bond between the two hydrogens, and that bond is described as a covalent bond where we are sharing electrons. And so that rationale or that description is discussing the intramolecular forces between hydrogen 1 and hydrogen 2, these two atoms. Now, what this chapter is concerned about is intermolecular forces. So the question becomes, is if I have this entire hydrogen molecule and I have another hydrogen molecule, how do these two molecules interact with each other? What are the attractive forces and what is the strength of the attractive forces between these two molecules? So when I'm talking about intermolecular forces, I want the molecule and I want a description of that molecule interacting with another molecule. I am not interested in breaking bonds or forming bonds so the molecule remains intact. When we talk about intermolecular forces, these are much weaker forces, but what is interesting about them is they give rise to the bulk properties of our substances. This is why things are liquids, why they're solids, why they are gases. So on that note, let's take a look at the relative strength between intramolecular forces and intermolecular forces. So on top right here, these are what are classically regarded as intramolecular forces. This is how one atom is attached to another atom. And you can see that these are quite strong, anywhere from 200 to 600 kilojoules per mole. Now on the bottom, what you guys will see are the intermolecular forces, or the classical intermolecular forces, hydrogen bonds, dipole-dipole, and London dispersion forces. And these are much weaker. They're about 100 times, and at best, maybe 10 times less than the intramolecular forces. Now, one thing that's kind of strange is the ionic bonds, and sometimes people will consider these intermolecular forces. So when I talk about an ionic compound like NaCl, remember that this is an empirical formula, and really what I'm talking about is how that sodium and chloride are ratioed together. And so because intermolecular forces describe bulk properties, well, there's not like a single molecule of NaCl. It's just this huge ensemble, trillions and trillions of molecules put together. So be very careful with what type of book you're working with or what kind of homework program you're working with, because sometimes people will just say forces and they want you to include ionic bonds when talking about things like boiling point or bulk property. So let's go ahead and hit our first quiz. Take a look at these substances and tell me which do you believe has the strongest intermolecular forces. So remember what we're saying with intermolecular forces. What I have is a molecule and another molecule, and I'm looking at the attractive forces between these things. So the greater my intermolecular forces are, what you can kind of say is the molecules are more sticky. They're more attracted to each other. The greater their intermolecular forces are, the more that they want to touch each other and interact with each other. And so when you look at gases, these molecules are not touching each other. They are not sticking to each other. So when we look at liquids, what we'll see is that the molecules are actually physically touching each other. They're rolling past each other. But lastly, if we take a look at our solids, these things have such attractive forces. They are so sticky that all my molecules are locked in place. So it has the strongest intermolecular force. Now, gentle people, I need you guys to do me a favor. So before you guys move on with chapter 16, it is imperative that you guys remember how to decipher if a molecule is polar or not. And what that means is you have to remember the topics that we've covered in chapter 13. Now, Chem 1A is a long time ago, so it'd be a good idea to review that material. What I want you guys to remember is that if you draw the Lewis dot structure, this does not tell you if a molecule is polar or not. You have to go ahead and tell me what the molecular geometry is, and then based off that molecular geometry, you have to draw dipole arrows. Once you have drawn those dipole arrows, you have to ask yourself, is there a net dipole present in that molecule? If there is a net dipole present, that means the molecule is polar. So if you guys had me in Chem 1A, here's the flow chart I provided to you guys to decipher if something is polar or not. It tells you at every stage what you can discern from the molecule based on the picture you have drawn. So please make sure that you can identify polar and non-polar molecules. So let's talk about two molecules as a mini review. First, let's draw the Lewis dot structure of carbon dioxide, and then let's go ahead and draw the Lewis dot structure of water. So that's going to be H2O, and here are the Lewis dot structures. So remember, the Lewis dot structures cannot tell you if a molecule is polar or not. You have to draw the molecular geometry. So carbon dioxide is a linear molecule. Now, once you've drawn the molecular geometry, you have to draw dipole arrows. And that is going to be based off the electronegativity of each atom. So remember, electronegativity is the ability for an atom to pull electrons towards itself while in a chemical bond. Fluorine is the most electronegative atom, and as you move down from fluorine and to the left and right of fluorine, you become less and less electronegative. So let's go ahead and take a look at this. What we'll note is that oxygen is more electronegative than carbon. So what I would do is I would draw dipole arrows with the heads of the arrows pointed towards the oxygen, and then the tails with that hash mark, that is going to be placed on carbon itself. Now, what you can see is that these dipole arrows are pointed in opposite directions, and they have equal strength going in those opposite directions. So this molecule, what you can say is that the dipole arrows cancel each other out. So in this case, there is no net dipole, and that means the molecule is non-polar. So another way to think of this is if you guys think of a tug of war, picture two people at either end, and because they are pulling exactly in opposite directions with equal strength, the molecule does not move, and if it does not move, it is non-polar. Now let's take a look at water, which we know is a polar molecule. Now we can explain why water is a polar molecule because we know that oxygen is more electronegative than hydrogen. If oxygen's more electronegative than hydrogen, we can draw our dipole arrows from hydrogen to oxygen. Now what you guys will see is that both of these arrows are pointing to the right. That means that there is a net dipole moving to the right side. Again, if I wanted to use my tug of war example, you have two people, one that is pulling up and to the right, and the other one that is pulling down and to the right. And if they're both pulling to the right, the molecule moves to the right. So this net dipole is going to lead to us having a polar molecule. Now, what this means when I have a polar molecule is you can envision that the molecule is a mini bar magnet, where it has one side that is positive and one side that is negative. And this is what's going to give rise to the intermolecular forces. Now, one rule that I can give you guys is that if you draw the molecular geometry and it results in the molecular geometry having no lone pairs around that central atom and all the surrounding atoms are the same atom around that central atom, then the molecule will have no net dipole. It will be a nonpolar molecule. Now, the converse of the statement is not true, meaning that if just because you have lone pairs or just because you have different atoms around the molecule doesn't make it a polar molecule. If you are on that scenario, you have to actually draw it out and double check if the dipole arrows cancel each other out or not. So let's talk about our intermolecular forces. So the first force that I want to talk to you guys about is dipole-dipole intermolecular forces, or simply just saying dipole-dipole forces. Now, these are going to be the forces found in polar molecules. So again, remember, a polar molecule you can envision as a little bar magnet. So if I have my little bar magnet, what you can envision is every molecule that's polar behaves like this bar magnet. So think about what happens is if you had, let's say, 10 or 20 bar magnets in your hand and you threw these bar magnets across the floor. Well, what would happen is these bar magnets would start attracting each other, they would start pushing each other away, and they would arrange themselves based on the dipole or the net dipole that this molecule has. Meaning the positive ends to these molecules would try to line up with the negative ends to the molecule, and the negative ends would end up being around the positive ends. Now, we can have two molecules be on top of each other like this, or another way that these molecules can be are end to end. And again, we have the negative end and the positive end pointed towards each other. So these are the attractive forces that are going to arrange my molecules. So when I throw them across the floor, what you will see is the attractive forces will arrange the molecules. These molecules are sticky molecules. They want to come together and they want to attract each other. Now, again, this attraction is fairly weak. It's 100 times less than a chemical bond, but it is still an attraction. So you can think it is a very weak bar magnet. Again, remember that these intermolecular forces, they are going to give rise to bulk properties. And this is how we see intermolecular forces arise and are able to observe them. So one bulk property that we can look at when describing intermolecular forces or seeing how intermolecular forces affect these bulk properties is the boiling point. So again, let's talk about two molecules and how they interact with each other. So what's happening here is there are attractive forces. So these are my intermolecular forces. They are going to want to drive that molecule together. Now, what also is occurring is that these molecules have kinetic energy. And the kinetic energy is going to want to make these molecules fly apart. Now, it doesn't necessarily mean apart that it's a repulsive force. What I'm trying to say is the kinetic energy is going to make these molecules vibrate and move, and they just want to fly off in any old direction. So what you have are two competing forces. You have the kinetic energy that is trying to take these molecules apart from each other, and then you have the IMFs trying to bring them together. And so these two forces are battling each other. Now, if my intermolecular forces are very, very strong, that means the molecule is going to try to stick together, and they are going to be sticky and attract each other, and they are going to want to touch and interact with each other. And so that is going to lead to states like liquids and solids. On the other hand, if my kinetic energy is so great, Well, what's going to happen is that no matter the stickiness of this, my kinetic energy or the vibration of these molecules are so great, they're going to force these molecules apart and they're going to go flying off in every direction, meaning they will not stick together and they will behave more like a gas. So this conflict is going to give rise to a bulk property, namely the boiling point. This is the point where the molecules behave like a gas, or they will act like the condensed states, like liquids and solids. Now, if I have greater intermolecular forces, that means the molecules are going to be super sticky. Now, to overcome this stickiness, what I'm going to have to do is give it more kinetic energy, meaning I have to raise the temperature. If I raise the temperature, give my molecules more heat, then I increase its kinetic energy, and then I will have my molecules boil off or fly apart from each other. So in other words, the greater my intermolecular forces are, the greater my boiling point will be. So let's look at a real world example. So here we have N2, and this is a non-polar molecule, which means it has no dipole-dipole forces. O2, again, a non-polar molecule, and it has no dipole-dipole forces. But in the middle right here, we have a polar molecule. Now remember, if my molecule is polar, that means it has dipole-dipole intermolecular forces. Now you can also see this by the delta electronegativity. Polar molecules are going to have a non-zero delta electronegativity. Let's look at the boiling points of these three molecules. What you'll notice is the one with the highest boiling point is the one that has the dipole-dipole forces, or the more intermolecular forces. So this is the manifestation of having intermolecular forces, meaning it has a higher boiling point. Now, what you might be asking is, these things are nonpolar molecules. Why can these molecules even stick to each other if they are not behaving like bar magnets? What's the attractive forces between nonpolar molecules? Now, there is an intermolecular force that is present in every molecule, whether it is polar or nonpolar, and it is called the London dispersion force. Now, this force goes by many different names. Some people call it the induced dipole. I've seen it other times described as the van der Waals force. So I just want you guys to note these things, but I'm going to refer to them as the London dispersion force, or LDFs. Now, LDFs are responsible for nonpolar substances becoming solids and liquids. LDFs are the only force present in these nonpolar molecules. Now, LDFs are super weak. They're about half as strong as a dipole-dipole force. Now, you can increase the strength of your LDFs, and there are two factors when trying to gauge how strong an LDF force is. The bigger the atom is, the greater your London dispersion forces is, and the longer or the more elongated your molecule is, the greater the LDF forces are. But let's talk about why this force arises and how it makes nonpolar molecules attracted to each other. Let's go ahead and use H2 as an example of how London dispersion forces work. Now, each hydrogen molecule is composed of 2 protons and 2 electrons. Now, because of probability and its distribution, those 2 electrons are evenly spread across the molecule. But again, that's the most probable arrangement of these electrons. There's a small probability that those 2 electrons will be on the same side of that molecule. If that happens, well, one side of the molecule is going to be negatively charged, and the other side of the molecule is going to be positively charged. So what I'm going to create is an instantaneous dipole. And what that means is this molecule is going to be, for an instant, going to be a bar magnet. Now, this doesn't happen all the time. This is just going to be fleeting in time, just a snap of my fingers. Now, when this occurs, let's say that two hydrogen atoms are next to each other. Now, what's going to happen is the electrons in this hydrogen, well, they'll be attracted to the positive charge of the other hydrogen. Now, if that occurs, then my electrons are going to slosh over here, and I'm going to have a positive end to my molecule, so I'm going to create an induced dipole. So this instantaneous dipole creates an induced dipole, and now for an instant, I have two bar magnets. If this is the case, these two molecules can attract each other. Now, to increase the chance of a nonpolar molecule having electrons that are not evenly distributed, well, the more electrons I have, there's more of a chance where the electrons will be unevenly distributed. The greater the molar mass my compound has, the greater number of electrons it's going to possess. The greater number of electrons it possesses, the greater the chance those electrons will be distributed unevenly, meaning greater London dispersion forces. And so this is the crux of having a bigger atom or a bigger molecule having greater London dispersion forces. Now, the other thing that can increase the amount of London dispersion forces you have is the elongation of a molecule. So take a look at these two compounds. They have the same molar mass because they're composed of the same atoms, 5 carbons and 12 hydrogens. Now, what is different about these two molecules is the way my atoms are arranged. In this top molecule, all my carbons are in a row. So to kind of exaggerate how this molecule looks like, it looks like a big bar like so. The second molecule we have, well, I have a central carbon, and then all my other carbons kind of radiate out from that center. So to kind of show you how this one looks like, and to depict it, it kind of looks like a box. Now, what's going to occur with this is that this one is more elongated, so there's more of a chance for the electrons to slosh to one side, making this more of a bar magnet where there's a greater disparity of a negative side and a positive side. The same cannot really be said for this. So the take-home message from this: long molecules are going to have higher boiling points than molecules that are shorter, assuming that they are composed of the same type of atoms and the same number of atoms. All right, let's go ahead and discuss the last intermolecular force. Now, this intermolecular force is the strongest of all the intermolecular forces, basically by a factor of 10. In fact, this molecular force really is just a dipole-dipole intermolecular force, but it is a special type of dipole-dipole. And because it's so strong, we consider it a new force. And this is called the hydrogen bond. Now, to have a hydrogen bond, what you need to have happen is hydrogen directly attached to an N, O, or F. These are some of the most electronegative atoms on the periodic table. And the reason this hydrogen bond works is because we'll note that hydrogen only has one electron. So if it is attached to something that is very electronegative, well, that electron is going to be shuttled over to that. And what's going to happen is that electron is going to spend most of its time around that more electronegative atom. So what's going to happen is the hydrogen, which has only one electron, is going to be laid bare, where the electron is going to spend most of its time on the other side. This makes this a really big positive and this a really big negative. And so as I make that difference in electronegativity bigger and bigger, my dipole-dipole forces increase, and these are the strongest dipole-dipole forces. Now, I want you guys to be careful. We have to have hydrogen attached to either a nitrogen, oxygen, or fluorine for this to occur. For example, if you had this molecule right here, this molecule does not have hydrogen bonding. Even though it has a hydrogen and an oxygen, they are not attached to each other. To get this special condition, what I need to have happen is I need that hydrogen to be directly attached, and then I will get this special type of dipole-dipole, the hydrogen bond. Now, just to show you how great the hydrogen bonding is, take a look at these series of compounds. This is the elements in group 6A attached to 2 hydrogens. Now, what you guys will see, sulfur, selenium, tellurium, these are bigger molecules. So as I go down, I increase my LDF forces, and you guys can see that my LDF forces increase my boiling point. The bigger my molecule, the bigger my LDFs, the higher my boiling point is going to be. However, there is one outlier in here, and that happens to be with H2O. Now, H2O is the only molecule here with hydrogen bonding. And because it has that special dipole-dipole, it has the greatest amount of intermolecular forces, and that means it has the highest boiling point. All right, gentle people, why don't you guys take a look at this quiz question, and what I want you guys to do is tell me which of these ones only has LDF forces. And as an exercise, go ahead and write down all the forces that would influence the boiling point of these compounds. Okay, ladies and gentlemen, let's tackle these one by one. So the first compound you guys have is going to be argon. Now, argon is a noble gas, and the only intermolecular forces that noble gases have by themselves are going to be LDF forces. So I'm going to go ahead and skip 2 real quick, and I just want to tackle 3, and I'll go back to 2 in just a second. So what I want to go ahead and do is draw SO2 out. So if you guys want to go ahead and draw the Lewis dot structure to this thing, this would be the Lewis dot structure. So remember what I told you guys before, we don't want to draw Lewis dot structure, we want to draw molecular geometry. And so this is a bent molecule. What you guys will note is that oxygen is going to be more electronegative than sulfur, and what you guys will see is you have a net dipole in this molecule. So this is a polar molecule. So a polar molecule are going to have dipole-dipole forces, and remember, every molecule has LDF intermolecular forces. So those are the 2 forces in that molecule. Let's go ahead and take a look at number 4. Now, this molecule has 2 of the same atoms, so there is no net dipole, so this is a non-polar molecule. So, like I said, every molecule has LDFs. Since it's not polar, it doesn't have dipole-dipole. So let's do number 5, and that's going to be NH3. So let's quickly draw the Lewis dot structure to NH3. But remember, what we really care about is our molecular geometry. So an easy way to do the molecular geometry of this one is to first draw the electronic geometry. So we'll put nitrogen in the middle, steric number 4. So that means our electronic geometry is going to be tetrahedral. But our molecular geometry, once we put our lone pair on there, our molecular geometry is going to be trigonal pyramidal. Now, if we take a look at this, we'll notice that nitrogen is going to be more electronegative. So I'll draw my dipole arrows up, all of them up towards nitrogen, and that means that there's a net dipole going up. So this is a polar molecule. So if it's polar, that means it has dipole-dipole forces. It's a molecule, so it has LDF, and this actually has one more type of intermolecular force. You will notice that it has a hydrogen attached to one of the most electronegative atoms, so this molecule has H bond. And so if we take a look at our list, that means 1 and 4 are only made of LDF forces. Now let's go ahead and tackle number 2, just so we can show you that that does not have just LDF forces. So number 2 was that one kind of case that I want you guys to be careful of. Now this molecule is an ionic compound, meaning I have lithium plus, and these things are charged ions, and they are surrounding a sulfate that is negatively 2 charged. The way this molecule is put together are through ionic bonds. But remember, when I give you the formula Li2SO4, that this is an empirical formula. And what that means is that there are multiple Li pluses all strung together, all stuck together as one big thing. So there are trillions and trillions of lithiums and sulfates put together. Now that means that this is a big honking molecule, and to actually get it to break apart, to get lithiums and sulfates to fly apart, I have to break ionic bonds, and ionic bonds are much, much stronger than any intermolecular force. Remember, this is about 100 times stronger than a dipole-dipole force. So this is the strongest thing that is keeping my bulk material together. It will have the highest boiling point. When I say the factors in determining boiling point, well, LDF isn't the only thing determining the boiling point in this. It's actually the ionic bonds that are determining the boiling point for this material. And so finally we get to our answer. There are only 2 of these where LDFs are the only factor in boiling point: argon and Br2. So I hope that made sense to you all. And remember, Chem 1C, to stay safe.